So this video is going to be about the non-ideal operational amplifier, or the non-ideal op amp. So in the video we're going to be going over the properties of the non-ideal op amp, how it's similar to the ideal op amp, but some things that are different when you're actually using one in a real circuit. Then we're going to be going over an example that involves a non-ideal diode, and then we're going to be going over something called the common mode rejection ratio. So now we're going to move on to talking about the non-ideal op amp properties. Okay, so now we're going to be looking at the non-ideal op amp properties. So the first big change when it comes to the non-ideal properties is the internal resistance. So because there is some resistance here, in an ideal diode, the resistance here is essentially infinite, which means that there isn't going to be any current flowing through here. But because you can't have actually infinite resistance, there is going to be a small amount of current that flows through one terminal and out of the other one. Another change is that there is going to be an output resistance. And in an ideal op amp, the output resistance is 0. And you can't have that for a real circuit device, so there's always going to be some amount of output resistance. It's usually somewhere between 50 ohms and 75 ohms. And also for the internal gain of the op amp, in an ideal op amp, the internal gain is essentially infinite. But again, you can't have infinite gain. So generally, the typical op amp internal gain is around 200 volts per millivolt. So when you are doing circuit analysis involving an op amp, you have to take these internal resistances into account while you're solving problems involving an op amp. So what we're going to do now is we are going to look at a problem that involves the non-ideal op amp. Okay, so now we're going to be looking at this problem that involves a non-ideal op amp. So the question is, what is the voltage gain that is supposed to be seen across the circuit? With VCC equal to 12 volts, is the actual voltage gain equal to the calculated voltage gain? The first thing that we're going to need to do is redraw our circuit so that it accurately shows the internal resistances of our op amp, so that we can use KCL and KVL to solve for the voltages and the currents. Okay, so now that we have our redrawn circuit, we are going to try and solve for the gain. So the first thing that we can do is we can find some relationships. So we can call this current here I1. We can call this current here that goes through the input resistance I2, and we can call the current that flows through here I3. So what we know, because of KCO, I1 is going to be equal to I2 plus I3. And we're going to call this voltage here V1 and this voltage here V plus, because this is at the non-inverting terminal. So we can see that I2 is going to be equivalent, using KCL, the voltage across here is V1 minus V plus divided by the resistance, which is going to be 1 mega ohm, as we stated in a previous slide. I1 is going to be equivalent to the voltage across this resistor, which is going to be 0 volts minus V1 divided by 1 kilo ohm, and where I3 is going to be equivalent to the voltage across this resistor, which is going to be V1 minus Vout divided by the 2 kilo ohm resistor. So now we want to put these into our relationship up here. So we're going to drop this 0. We're going to say that I1, which is negative V1 divided by 1 kilo ohm, is equal to I2, which is V1 minus V plus over 1 mega ohm plus V1 minus V out divided by 2 kilo ohms. And we're going to multiply by a common multiple on both sides of our equation, and that is going to be 2 mega ohms, which 2 mega ohms times 1 kilo ohm is going to give us negative 2000 V1, which is going to be equal to 2 mega ohms divided by 1 mega ohm is going to give us 2, which we're going to distribute to V1 and minus V plus. So it's going to be 2 V1 minus 2 V plus. And then 2 mega ohms divided by 2 kilo ohms is going to give us 1000, and we're going to distribute that to V1 and V out, which is going to be plus 1000 V1 minus 1000 V out. So we're going to clear the screen and keep working on this. Okay, so the next thing that we're going to want to do is try to get V1 by itself on one side, because we're going to eventually try and cancel it out. So what we're going to do is we're going to move all of the V1s over to one side. So as you can see here, we have a 2V1 and a 1000 V1. So what we can do is we can combine those together to be 1002 V1, and we'll just subtract by that on both sides. So we're going to subtract by 1002 V1 on both sides. Okay, so 2000 minus 1002 is going to give us minus 3002 V1, and then this 1002 is going to cancel out the 2V1 and the 1000 V1, and this is going to give us this, which is going to be negative 2 V plus minus 1000 V out. And we're going to divide by negative 3002 on both sides. And what that's going to leave us with is V1 equals 2 over 3002 V plus 1000 over 3002 V out. And so this is going to be one of the equations that we end up using. And so now we need to use this node to find our other equation. So we're going to call this current now I4 and this current I5. So the currents entering and leaving a node all have to be equal to each other. So we know that I4 has to be equal to I5. Now looking at this, we can see that I4 is the voltage across the 2 kilo ohm resistor divided by that 2 kilo ohm. So the voltage across the 2 kilo ohm resistor is going to be V out minus V1 divided by 2 kilo ohms, where I5 is going to be equal to the voltage across our R out, which is AV in minus V out over our output resistance, which is going to be 75 ohms. And so we're going to use these equations to find our next equation. So we're going to clear the screen now and keep working. Okay, so now we have our equations here, and we're actually going to simplify I5 real quick. So we know that AV is going to be 200 volts per millivolt, or we can treat that as 200,000. So we can say that I5 is going to be equal to 200,000 times, and Vin is actually going to be the voltage across our I. So that's going to be V plus minus V1. We're still subtracting our output voltage. And this is all divisible by, or being divided by 75 ohms. So now we're going to set these two equal to each other. So we have V out minus V1 divided by 2 kilo ohms is equal to 200,000. I'm not going to distribute it just to save space. Minus V out all over 75 ohms. So now I'm going to multiply on both sides by a common multiple of these, which would be 6k. So if you multiply on 6k on this side, you get 6k divided by 2k, which will give you 3. And then you have to distribute the 3 to the V out and the minus V1. So you have 3 V out minus 3 V1. This is going to give you 80. 6k divided by 75 is going to give you 80, and 80 times 200,000 is actually going to give you 16 times 10 to the 6. So we'll write that 16 times 10 to the 6 times V plus minus V1 minus, and then we have to distribute the 80 to this V out as well, which will give us 80 V out. And one thing we can do is we can add the 80 V out to both sides. And that's going to give us 83 V out minus 3 V1 is equal to 16 times 10 to the 6 times V plus minus V1. And again, we're going to clear the screen and keep working. Okay, so now we have this equation, and what we want to do is get V1 by itself again. So what we can do is we can distribute this 16 million to both, and then we can move this V plus over to this side and move the 3 V1 to this side. And so what you get when you do that is you get 83 V out. We're going to add our 3 V1 to both sides. That's going to give us 16 times 10 to the 6 V plus minus 999,997 V1. And so we can also move this 16 times 10 to the 6 V plus over to the other side. So we'll subtract that. And so what you get is negative 15,999,997 V1, which is equal to 83 V out minus 16 times 10 to the 6 V plus. And then we can divide by negative 15,999,997 on both sides. And that is going to give us V1 equals 83 over negative 15,999,997 V out plus 16 times 10 to the 6 divided by negative 15,999,997 V plus. And this should actually also be positive. And what we're going to do now is we're going to take this equation and we're going to combine it with the other equation we got from using our first node to solve for the gain of our circuit. Okay, so now we're going to subtract our equations so we can solve for the gain. So when we subtract our V1s, we're going to get 0. And when we subtract our V plus terms, we are going to get 0.9993 V plus. And when we subtract our V out terms, we are going to get minus 0.3331 V out. And so we can add 0.3331 V out to both sides. And what you get is 0.3331 V out equals 0.9993 V plus. And now what we're going to do is we're just going to get our gain by itself. So we'll divide by V plus and 0.3331 on both sides. Our V pluses are going to cancel out on this side. Our 0.3331s are going to cancel out on this side. And what you end up with is V out over V plus, and that is approximately equal to 3. And so with this, our gain is going to be 3 volts per volt. Now, we haven't entirely answered the question yet, because now we've shown what the gain is supposed to be, but is the gain actually going to look like this? So now we're going to go back and look at what the original diagram looks like. So what it says here is with VCC equal to 12 volts, is the actual voltage gain equal to the calculated voltage gain? Now, the actual voltage gain is not going to be equal to the calculated voltage gain, and here's why. With the way that an actual op-amp works, you need to provide it with a supply of voltage, and that's what the VCCs are. So the maximum output voltage that this can create is going to be whatever the maximum voltage is at VCC. So the highest voltage is going to be 12 volts and the lowest voltage is going to be minus 12 volts because of the way that our power supply is set up. So, and with our 3 volt per volt gain, our output voltage is supposed to be 30 volts, but we are going to saturate at 12 volts. And saturating is when you hit that upper limit of how much voltage you can gain out of your circuit. So, no, the actual voltage gain is not going to be 3 volts per volt with our 10 volt input. So, in this video, we discussed the different properties of a non-ideal diode, and we went over an example problem dealing with the non-ideal diode.